I wanted to start out just to quickly just get a show of hands on kind of the people in the room, so I know a little bit about how to kind of guide maybe a tad bit of this. So if you are a resident or medical student, do you mind raising your hand? Okay. And then if you're an attending or any other kind of level, do you mind raising your hand? Okay, there's that. And then who here has done coding or statistical work or anything like that? So, okay, so most people, so that's good. Okay. So what we're going to talk about today is reproducibility and emergency medicine research. This is just a tad bit of background about myself. I'm an assistant professor of emergency medicine at Yale, and I'm the director of clinical informatics and analytics there. So I wanted to first kind of give a picture where at least I kind of think that emergency medicine research is currently at. You can correct me if you think I'm wrong, but this is the kind of picture that I see on a day-to-day basis and the experience kind of as I was initially starting up as a researcher. So it's this idea that you have some idea or research topic, and you have some mode of data collection, whether that's a clinical trial, whether that's a survey, whether it's you're pulling out data from the electronic health record. And then there's some process that pulls in that data into some particular spot. And you may pull it into Excel, you may put it in a CSV in some file or folder, and then somebody that's on the research team does some initial kind of data processing. They're looking through the data, they're kind of cleaning it up, and they may be doing that in Excel. They may be doing that in a programming language like R or Python or something like that. And they get it to some point, and they meet back with the research team, and they kind of discuss it. They kind of resolve out some issues, and they finally get it to some point where they feel like, okay, it's clean enough. We can now send it to the statistician. It gets sent over to the statistician. They look at it. They're like, oh, no, this is not in the format or anything else that I need. So they do some more manipulation with the data, and they finally get it to the format that they can run their code on and do whatever kind of statistical analysis they need to do on it. And they keep that kind of black boxed. They then return whatever results the researchers wanted to kind of get out of the research to the research team. And that's usually probably a few tables, a few kind of demographic information and some particular outcome variables. That research team then goes about kind of manipulating the manuscript, never actually having seen kind of any of the analytic work that's being done. They create figures in Excel, and they're using whatever form they're wanting to do, and that's being done in some other location. Finally, they get the manuscript kind of all crafted. They submit it to a journal. It gets accepted. Luckily, at some place you don't have to go through multiple revisions. And then they shut down the process. Nobody ever sees the data again. During the submission process, nobody sees the code. Nobody sees anything of the data itself. If that sounds familiar, you're in the right place, because I think there's a different way of going about this. So I wanted to briefly touch on two definitional aspects before we kind of further went into discussion in this talk. One is about, these are two ideas, and they're kind of bandied about within the literature, and I think it's important to be clear about these definitions. So replicability in this context is really about taking a research idea and then using that similar type of protocol and going to a different location to kind of replicate those results. Reproducibility, I think, is much more akin to what I would consider kind of computational reproducibility, in that you have your data set, and you're trying to get to the end result that they got to using that initial data set. And I would group that into reproducibility, the other one into replicability. They do have some overlap. Obviously, if you don't have very reproducible computational steps, it's going to be really hard to replicate that, and even in some external environment. But just keep those in mind as we go through. And so, I don't think this is just an emergency medicine problem, and I think that's indicative of a lot of surveys and kind of information that came out over the last probably 3 or 4 years. There was a pretty prominent survey that was done in the journal Nature, where they surveyed like almost 1,600 researchers, and it was like across like a wide spectrum. There were people in physics and bioinformatics and a lot of other fields. But they basically asked them, do you think there's a reproducibility crisis? And there was some overlap with replicability in that kind of in that question, but over 52% said yes, and then an additional 38% said yes, there's a slight crisis. So there was only 10% of people that even thought that, like, no, there's not a problem. And there was some more disturbing, what I thought were more disturbing kind of answers that came out of that was that 70% of the respondents had tried to reproduce somebody else's results and it failed. And then over 50% of people had tried to reproduce their own results in some other context and it failed. So I think that there's definitely a problem, and I think that there's a better approach for going about this. And so around the same time that all of this was coming out, I think there was a lot of initial discussion, and it's ongoing, and a lot of development in this idea about computational reproducibility and an open science framework, and that's what we're going to talk briefly about today. So we're going to describe some of the concepts behind open science. We're going to describe just a few best practices for open code, and I don't expect really anybody to become a coder. I don't think it's necessary. It may be necessary in the future, but right now I think you can get away with not being able to code well. But I do think that you should have some kind of analytic interest in what your statistician or somebody else that's doing the code for you, what they're up to. And that may be, if it's well documented code, you can go through that. We're going to talk a little bit about that. We're going to discuss dynamic data documents, which is this kind of idea about really tying kind of software to the documents or manuscripts that you're outputting. And then last, we're going to talk about some issues that you run in with just working with software and how to kind of manage that with scientific containers. So I'm sure you're quite aware medicine is exploding as far as the kind of the amount of information that's out there. I think you could start to view things in medicine as being more of an information science. We're getting data from all over the place, whether it's genomics or metabolomics or tons of EHR data, whether it's from clinical trial networks or distributed research networks that are using EHR data. There's data now that we're piping in from social media. So there's a lot of data out there and a lot of things to be able to do. And even in emergency medicine, I'm seeing this more and more. I think we have CEDAR with Equal. There's some large kind of research networks that are forming, looking at some quality things. I even read a recent paper on some biobanking stuff for looking at genomics in the future. So I think that this is within our sphere as well, and we need to know really how to handle all of this stuff. And so because of this information explosion, you really run into problems about kind of how to handle this. There's multiple different types of data sources. Like Twitter data is very different than EHR data, which is a lot different than clinical trial type data, where it's not usually nice and kind of clean. In addition to that, if you're looking at the data, it can be also in a lot of different formats. You can have areas where you have kind of graph-based data and network data. And all of that stuff is generating kind of new methods and creating increased demands on researchers. And I think problems with kind of just general methodology. And in addition to all of that, because there's all this data out there, there's tons of research going on. And because the submission process, I think, has gotten easier as we become more electronically savvy. There's increasing journal submissions. And that, in turn, creates this demand and pressure on statisticians and reviewers. And they don't really have the time to go through and really kind of truly review a lot of this stuff. And so that all of these things contribute kind of to this reproducibility problem. So we're going to talk about open science. And what's the idea behind open science? I think it's well described by the initial word, which is open, and that means a variety of different things. It means open data, so de-identifying your data and putting it out there in some form that other people can use. It means having open notebooks where you actually see kind of the analytic work that's ongoing and the kind of the manuscripts that are generated out of that. It means open peer review processes where you're having people that are actually putting their names on things. I think that peer reviewers should be able to be graded. There's a lot of different concepts with that. It's also putting open source code out there, open educational sources, and all scientific social networks. So a lot of ideas kind of around just really, I think the idea is that you should be doing research, and you should be doing research in a way that you anticipate that somebody's going to be looking at every step of your research along the way. And that, I think, drives good quality research. And there's growing support for kind of the open science movement within medicine. I think a number of researchers have found it beneficial. It tends to create more collaborative environments. There's a lot of good now tools and publishing environments that help you with this. So there's very good tools for collaborating with using code. There's very good tools for now doing even manuscript writing and other things. A lot of the funders, particularly I think the government is taking a lead on this, are requiring you to have some type of open data kind of policy when you initially start your research. And then I think while this is lacking to some degree, there is some recognition in academic kind of evaluations. If you're contributing to some meaningful project and you're providing code within that space, that is kind of, I think, growing up, but it's starting to happen. So I think the other idea behind the open science is the idea of a pipeline, and we talked about initially with that kind of, I would say, kind of hodgepodge of different kind of steps that I think research is kind of currently in this situation. So an open science pipeline is this very different idea where it's basically you should be able to hit a button and go from the raw data that's initially collected to the outputs of the manuscripts at the end, and never do anything, and never have to touch a button, like other than that initial button. That's the way the pipeline should be created. Everything along that pipeline should be automated. And that's going to enhance your reproducibility. So you have your data on the side, you have your code that's interacting with the raw data. At some point you pull out your de-identified data. That's going to be put into an open science repository. The code that's interacting with the raw data, you're generating dynamic documents that are coming out of that. Those are being put out as manuscripts. And then that information, along with the de-identified data, because it's sitting in a repository, enables further research that can generate additional manuscripts that are coming out of this. So, a key aspect of kind of the open science initiative is this kind of idea behind open data. And I saw like 4 kind of aspects to this, but 4 kind of maybe challenges as well. So one, you often hear, well, what's the patient perspective on this? And I look at it as like so when you do research, you're accessing somebody's data, you're putting them at some particular type of risk. Even if it's EHR, there's some type of security risk around that. The way to kind of, I think, faithfully do your research is to maximize that kind of risk or exposure, well, to minimize the risk or exposure, but to maximize the benefit that you get out of that research. And one way to do that is to allow the data that's generated through the research process to be open so that other researchers can use it, generate new ideas, create new research off of it. So that's kind of the patient perspective that I have on this. The other thing that you have to be clear on with open data is you've got to remove PHI. So most of you are probably somewhat familiar with kind of the idea around protected health information, but you have to remove date time stamps, you've got to remove names, and really any other. It's pretty common sense kind of what components would be with that. The other thing that you may see and you may run into is your IRB regulatory issues. So I think you need to be very upfront about when you're kind of writing your IRB about what you're going to do with the data, what your intent is. Some IRBs are now including language about whether you're going to give this to secondary organizations, how you're going to use this data in the future. And I just think you need to have some language and guidance around that. And I think it's helpful just to talk with your IRB about how they see that process going on. It's going to be very different for like a clinical trials versus the research that I do, which is mainly in electronic health records, how that process occurs. And I think, for clinical trials, obviously you could frame some of the questions to the patient up front. For EHR data, if you're pulling out 1 million patient records, it's a little bit different. You can't go ask every one of the patients, so you've got to kind of frame your language around that. And the last is finding public repositories to put this data. There's a lot of good public repositories out there. It's not very hard to Google things and find some good scientific repositories to put those things into. So the other ideas with open code, I thought this quote was great. It said, software is it's as important to modern scientific research as telescopes and test tubes. And I truly believe this at this point. I think we're moving into a different age. And I wanted to talk about a few things. So one is organization around kind of your coding practices. You really should have some type of standardized process about where you're putting your data, where you're putting your kind of the code that is involved in creating your dynamic documents, where you're putting your code that's involved in the pre-processing step, and where you're putting your figures and everything else. And that should be pretty standardized. Obviously, if you're working with a large team, you're going to have to kind of agree on this, but those steps should be in place. And then the nice thing about that is once those steps are in place, it's not hard to then generate a new project, have that same process. A lot of your functions and things that you're doing off of that can just carried over into the next project. The other thing is about style. And again, this is not the expectation that you're going to be doing coding yourself, but you should ask of your statistician, your programmer, whoever's doing kind of the analytic work, that they write good code that is well documented, that has some type of functional style to it. And you want to be able to at least be able to look through the code and see kind of what's going on. Like you should be able to read through and say, oh, well, this function is doing this for our task. This is doing that for our task. I don't expect you'd be able to go through and figure out everything that's going on. But those are things you can ask of your statisticians or whoever doing that. Because if the statistician leaves, somebody else has to come on board. If somebody's then trying to read it in the future and replicate it or reproduce it, well-documented. You need well-documented code for people to be able to figure out what's going on. And then the last thing is version control. So I think a lot of us are familiar with this kind of in the manuscript part of things where somebody's writing something, they upload it to Dropbox, and then somebody else wrote something, but it was in a state where that person had saved it already, and then now you get one version, and then somebody else writes something, and now you've got like 4 or 5 versions out there. It becomes a disaster really quickly. There's Google Docs and some things that are that help with that, but there's also this idea in coding practices about versioning. It's a little more formalized. There's kind of this idea that there's this central kind of code repository, and that everybody can independently pull down the code and whatever they're working on, and then they make suggestions of changes to the kind of overarching documents, and then those are accepted or either rejected. But it's kind of keeping in track of all of those things. So you really should try to do something along those lines with the open code. So the other thing I wanted to talk about briefly was just dynamic documents. And this is the idea about treating kind of a manuscript-like software. And I'm going to just pull out of this just real quickly and show you kind of an example. If I can get it on the screen, I might not be able to. I didn't check for that. Hold on, let me do one thing. There we go. Okay, so I know it's small. I don't really expect you to be able to read the code, but the idea is that you have a set of basically code on one side that is generating your document and your output on the other. So it's entirely conceivable that you take your manuscript, you have code that's underlying it, it's generating all all of the inputs, even within the kind of results section, your demographics and your numbers, you go through all of that, and it's generating all of those numbers. The other really nice thing about this is that because there are HTML and other formats, you can have embedded stuff that has like tables that are able to be scrolled. You can have interactive visualizations and other things that are nice parts of that. So it's just this idea that you're kind of coupling the software with your output through your manuscript process. And then I'm going to drop in here real quick. Okay, and then one of the other things I wanted to talk about was just kind of the public repositories with the open code. Hopefully I can click on this and it'll move through. I'll pull this through as well. This is the problem when you have too many desktops. So this is one of our projects that we did, and we put it on GitHub. But really, the idea is that you put all your code on a particular site. So we have kind of all of the initial kind of saying where it's been committed to. So that's kind of the initial versioning process. You have some type of README file that's describing the project and everything else. You can, if you're doing particular work that you need to have copyrighted, you can put those things on GitHub and use those aspects. But it's just the idea that you're dumping stuff into a repository that other people can see and interact with. I'm going to pull back just for a second. Okay, and so then the last thing I wanted to talk about was scientific containers. So one of the problems that you run into when you're writing software and kind of running these analytic programs is that there's basically this issue of code rot, in the sense that you downloaded a software that was version 2.1. It initially worked with that, but now they've updated one aspect of the software, and anybody that comes kind of along in the future, even if they do everything else right, if they don't have the right software downloaded, they run into problems. They can't reproduce it. And so the idea behind scientific containers is that you kind of wrap all of your software. You can think of it kind of like as a box where everything is contained within it. All of your software downloads and dependencies are kind of in this nice little box. And then then people are able to download all those software dependencies and run the code that way, so that it kind of contains everything in this nice little format, and then hopefully you get over this issue of the versioning with the software and everything else. So I did want to speak just briefly about some limitations. So we did talk a little bit about the academic reward system. It takes a lot of effort to do this. And right now, there's more reward in just getting out publications than doing what I would say is good science. So there needs to be some kind of changes in that area. Generally, people have a reluctance in kind of publishing their code. I would say if you're not confident with the code that you're putting out there in the kind of the analytic process, you shouldn't be really confident in your research. And so, it's hard to get over that, but I can understand that. And then I think this is a more sinister kind of idea, is this idea about research parasites that, okay, I've put in all of this effort into generating this this data set, and it's kind of mine. And I want to be able to do all the research on it and generate all the manuscripts on it. And I don't want somebody just put out that code kind of online and then somebody else to be able to do all this research off of it, and that's their job. They don't have to do any of this data collection. I think you have to question why you're doing research in science to begin with. If this is meant to get it out there so that other people can learn information and help patients and generate new knowledge. But I understand those competing interests, and it's something I think we have to work on in the future. So in summary, I think just think about your research as an automated pipeline. It's really that idea that you should go from raw data to kind of final manuscripts in one button click. And then I would say, even if you're not doing coding or a lot of these steps, be invested in that analytic process. Really understand what's going on, and making sure that things are being done well in those particular aspects. So I'm going to stop there, and I'll entertain any questions before you have to move on. Yeah, sure, go ahead.
Yeah, so you mentioned that programming coding. That depends on different program software you use, right?
Right. Yeah, So even for the document, everything's going to depend on the software, and some of that is going to be team dependent. You're going to get a programmer or a particular data scientist or a statistician that likes one software versus the other, and it's tough. People like their kind of software that they work with, and it's tough when you have disparate team members working on different stuff.
So that software is specifically, referred to like a statistics software. Like the program that you show us, is that from like a?
That's from Python. Well, one of them was from R, one of them was from Python. Those are the two I use most frequently. Sure.
Yeah, this might seem like a little retro question, but that's where I am computer-wise. And then why are you focusing on sharing code rather than trying to duplicate someone's methodology, which is what I understand as being the main goal of reproducibility? And then if in fact they feel that in order to reproduce it, they need to have your code, they would pick up the phone, call you up, or email you, or whatever.
Yeah, so I would agree. So there's really two steps to the methodology. One is like if you're running a clinical trial, you have your method, your protocol, and that part of thing, how you're enrolling people, all of that. There's no reason why you couldn't put that all online as well. And a lot of times it has to be through registration through clinical trials and everything else. But the code itself is the methodology, and after you get through the data collection process. Once that data is collected, everything else after that is a computational step, and it can be documented in that way, and can be treated kind of like that moving forward. So I agree that there's two aspects. One is how you collect the data and how that initial part is set up, and then the second part is kind of the computational process moving forward after that.
So what you're focusing on is the process of getting the data, and that requires this computation tool.
This is the process after you have gotten the data. So this is after you've collected the data. This is what I'm suggesting. Using moving forward with.
So you've collected a bunch of data. I want to reproduce it. I go and look at your methodology. Do I have to use your same code then to do that, or wouldn't it be more robust if I created my own code and did my own process, and then we'd see whether we came up with the same result?
It's definitely so. There's different. Yeah.
Because in other words, your code may have a blind spot here. My code might have a blind spot here, and if I'm just taking your code rather than my code, we'll never learn about your blind spot.
Sure. No, definitely. There's different ways of doing checks on kind of the results, and that's definitely one way is to run taking the data and to running it in a different way or format and checking whether the results are the same. But you can't do that unless you have the data and you can find out why somebody came up with a different result in the future.
So you're talking about sharing data? I'm sorry.
Both sharing data and code. You share everything. That's the idea.
So you've collected a bunch of data.
You de-identify it, you share it, you put it out there. Everything goes.
I feel like a research parasite already.
It's okay.
I'm just sharing the data.
Yeah.
Why don't I then go to my institution and say, okay, I want to go and do this, reproduce what Andrew did,
Right.
and try and do the same.
Yeah. No. That would be.
I'm going to do it my own way, and I'm going to use my own methodology, and that way we'll see. Because we've sort of, by introducing this code thing, we put another step in the process of research, which is
Right.
you have your raw data, you have your data gathering. The next step, then you have your analysis of the data, and you're saying let's share the data gathering part. When that maybe, and it's usually in traditional research, that's usually what the problems are. Is that the methodology.
Yeah. I completely agree. That's a whole different ballgame about the data gathering process. But we'll stop there. I know other people need to get up. No, yeah, it's fine. Thank you all. I appreciate the questions.